Let's see. It should be starting in a minute now.
Want to start an online store quickly with products that are ready to sell? Head over.
So, yeah, let me fix that. I'm gonna wait for a couple of seconds. All right, let me just quickly check whether the stream works, but on my phone. All right, cool. So everything seems to work. And yeah, I guess I'm just gonna wait until I'm gonna wait for 1 minute because technically the stream should start in 1 minute. But I can also wait for a bit to see whether some more people will tune in. If not, I'm just gonna start it as it is. And yeah. All right. I mean, maybe I'm just gonna start because like in the beginning, I'm gonna explain what the problem asked for, and then I'm gonna go to the interesting part about like linked trees and how to implement them. So yeah, I guess let's just start with the problem. So yeah, basically the problem was from the last long challenge, like the first contest by CodeChef for this year, and yeah, it basically required matchings and linked trees, or at least that was the intended solution. After the contest, like one of the people who tested the problem actually found a solution that didn't really use linked trees, but I still decided to share the linked tree solution in the video editorial, mostly because like technically this was the intended solution, and I think linked trees in general are a pretty cool tool, which can solve quite a lot of problems if you understand them. And hopefully after the end of this video, you'll be able to understand them. So yeah, I guess let's just first start with the problem statement, and then I'm gonna go to like the solution, and then I'm gonna explain linked trees, but I mean, I'm gonna explain the general idea. I'm not gonna go so much into the proofs because like if you're interested about them, you can check them. And I decided to not go to the proofs, mostly because if I did, the video would have been quite long, and yeah. I mean, it will be quite long nonetheless, mostly because I'm going to implement the whole solution in the end of the video. So, actually, not the video, it's a stream. But yeah, I guess you get the point. Let me just quickly open the comments, if there are any, during the session. So, yeah, just 1 second. Right, so cool. Let's go to the problem statement. I think I have opened it here. Yeah, well, I have opened the contest here. Well, actually, it is the problem statement. All right, cool. So basically, the problem statement in the problem we are given two arrays, which are A and B, and the length of both arrays is n, and yeah, these two arrays, in some sense, will define our beautiful sequences. And by beautiful, the definition of beautiful is basically you pick some sequence, which is like you pick two sequences, and for every position, you can either pick the A value at this position or the B value at this position. And yeah, sequence is beautiful if and only if you can create such a sequence by choosing A's and B's, and in the end you want all of the values to be different. Like it's basically just you have a bunch of you have like the two arrays, and you want to choose whether for every position either the A value or the B value, and in the end you want all of the values to be different, like at all positions. And if this is possible, then some subsequence is considered beautiful. If it's not, then it's considered like not beautiful. And in our task, what we are asked is basically for every position, we want to find a value mi. I mean, in some sense, as I actually also tested this problem, I can explain what was the reason for this quite complicated problem statement. Basically, for every position, we want to find the maximal length of like a beautiful substring that ends at this position. Or in some sense, we want to like basically have something like a sliding window that corresponds to this beautiful subsequences. By subsequences, I mean continuous subsequences, such that like the elements are neighboring. And yeah, I mean, basically we want to calculate this mi, which is for every position I, it's like the maximal length to the left, such that the substring from I minus mi plus 1 until I is basically beautiful. And after you calculate those mi values, you're interested in finding the number of ways to create a beautiful sequence from I mean, you get like this subarray from I minus mi until position I, and you want to basically find the number of ways to create a beautiful subsequence from this subarray. All right, so basically that's like the problem statement. The final part of calculating the number of different ways to create this beautiful subsequence, this was mostly added because unfortunately there was this solution with incremental matching, which passed, and it's very hard to kill, especially because our graph for this problem turned out to be quite simple. But I mean, actually, let me go into the details. I think I tried doing my best in explaining what the problem statement asks. But in general, it was like, I mean, I'm gonna give basically the graph version now, because if I like talking about sequences is slightly more complicated, and yeah, it was basically, let me just start with the solution. I think I'm over-explaining myself a bit now, but yeah. All right, so basically first I'm going to start with the stupid solution, which is the matching solution. And that was basically the way you need to start the problem, so that, yeah. So when is actually one subsequence, or like a substring, good or beautiful? Well, the definition was, the main idea is we have to create a bipartite graph. On the left side, we'll have all of the positions, like from left to right, because our subsequence is from left to right. And on the other side, like the right side, we'll have basically just all integers, which are from like minus infinity to plus infinity. And let's add edges for every position. Oh shit. Oops, sorry. Okay, so I was just looking at the comments. Sorry about that. Okay, so going back to the matching solutions, basically for every position I, we basically have an edge from I to AI, and from the position I to BI. Or in some sense, we just have the bipartite graph. On the left side, we have all positions. On the right side, we have all integers. And we have an edge from every position to basically the two numbers. And in some sense, like, there is clearly a bijection between those bipartite graphs and like basically beautiful sequences, because like if this thing has a matching of size right minus left plus 1, or like a perfect matching for the left side, then obviously we can create a good sequence. So yeah, that's basically like the matching solution. And by incremental matching, I meant like the Kunz matching algorithm. So yeah, there was a small question. Do X represent positions in S? Yeah, basically here by X, I meant like basically the positions. And in some sense, for every position, you want to choose either AI or BI. So that's why we have like those edges. And then like Y is just like all of the integers from minus infinity to plus infinity. And if you have such a construction, then basically if we have a matching, then this means that the sequence is good because we can choose y values in such a way that none of them will basically like correspond to each other. I mean, like basically this is like the straightforward conversion of good sequences into like a definition with matching and bipartite graphs. But yeah, like there was this incremental matching solution, which was basically you just skip 2 pointers, and at every point you just try matching the right thing, and if you can, you basically just move the right pointer. If you can't, you just unmatch the leftmost thing, and yeah, you just start over. And yeah, unfortunately, this thing is fast enough if you just want to count the sliding. I mean, if you just want to, for every position, to count the maximal length of the matching, this is a sufficient solution. I mean, like, the time complexity is pretty bad, but it's very hard to kill. And I mean, I tried killing it and it was very hard. So in the end, we decided to complicate the problem a bit by actually requiring the number of different matchings, as then you can't really do anything with just matchings. You need to observe the structure of the graph. And I mean, like, basically, the main part of actually going to from a completely matching solution to something that is faster is to observe the specific structure of the graph, and mostly the part of that all vertices in X will have a degree at most 2. Well, this is basically by construction, because from every position in X, we have at most 2 edges, one to AI and one to BI. I'm saying at most 2 because there is the case where AI is equal to BI, and then we have just a single edge. And yeah, that's pretty much it about like the specific constraint of our graph, like the degree being 2. And this is actually pretty useful because so some people will probably be familiar with I mean, when you have a graph in which the degree of all vertices is 2, then finding the maximal matching is actually way easier than just reusing some matching algorithm. And like, I mean, I'm gonna basically open this problem from Codeforces, which is like an all problem. Also, I'm gonna add it in the chat. Yeah, just a second. I mean, okay, apparently I'm not sure whether I can add it here, but okay, like the code is 875. So yeah, I mean, yeah, basically this problem was asking for, you have such a graph where the degree of every vertex is 2. Basically from vertex I, we have like 2 edges to AI and BI, and then we have like this weight, and you wanted to find the maximal weight matching, where like weight was the vertex, the weight of the vertex. And I mean, like, this is even harder than just finding the maximal matching, because you want the matching with the maximal weight. And I mean, the trick here is to actually, I advise you to check this problem afterwards. It's also pretty interesting, although it doesn't really require any complicated data structures. In the one I'm showing right now on Codeforces, you could just use like a disjoint set union. But like, the main idea is that there is this trick of finding matchings of graphs when the degree is at most 2, and it's relatively simple. So let me go back to the slides. So the main idea is that basically we have 2 edges for every position, which are AI and BI. And yeah, like, that's why the degree is at most 2 for all vertices on the left side. And now we are gonna basically just create a new graph where for every position we'll add an edge between AI and BI. I mean, in some sense, like, we had this bipartite graph, and we create a new graph which won't be bipartite in this case. It will be just like a new graph where every position will basically, I mean, every position, which was like a vertex in X, will now represent an edge between AI and BI. And in some sense, for every edge, we can choose the direction. Because like, when you choose the direction of the edge, this means if the direction is from AI to BI, this means that we have chosen BI as I mean, this means that we have basically matched the position I with bi. And if we have chosen the direction of this edge to be from bi to ai, this will mean that we have matched the position I with ai. And now our observation is that a perfect matching exists for such a graph if every connected component is either a tree. So like for the first case is basically we have a tree, which means like we don't really have a cycles of AIs and BIs. And in this case, obviously when we have a tree, we can just fix one of the edges. And after we choose its direction, actually I'm going to explain it in a bit, but like, because we also need to consider how we are going to count the things. But like for a tree, imagine you choose a leaf, and there are two cases. The first case is that you choose the direction to be towards the leaf. In this case, the matching can be, in some sense, we can just remove this leaf and consider the other part of the tree. And in the second case, if we have chosen the other direction, basically not matching the leaf, then we can uniquely determine all other edges, like the directions of all other edges, because as I said, we have a bijection between perfect matchings and directions of the edges in our graph. So yeah, like if a connected component is just a tree, then we are basically fine, because then we can match the edge. Then we can choose the directions of the edges so that a matching will exist. Then like the second case would be if a component is a tree with one additional edge, and then we basically have like a tree with a cycle. And it turns out that this is basically the same, because in a way, like we have a cycle and we can just choose the direction of the cycle. And after we have chosen the direction of one of the edges in the cycle, everything else can be uniquely determined. So like when you have a tree plus one edge, there are two ways to match everything. And then what about like a tree plus two edges? Well, this actually means that we have two cycles, which maybe, they can be connected, but like if they're connected, it obviously, like after we choose the direction on the main cycle, then like the last edge, like we won't be able to match the last edge. And if the two cycles are disjoint, then we basically have the same problem. And it turns out that if we have a tree with two edges, or like a tree with two cycles, then there is no way to match everything. So in other words, the way, like when we have a graph with all of our degrees equal to 2, like on the left side, and like a bipartite graph, finding the perfect matching is relatively simple, mostly because a perfect matching will exist if and only if every component is either a tree or a tree with one added edge. And yeah, like this means that if you just want to find the maximal matching, you can just go through the edges and check whether they will create, if an edge basically just unites two components, this means that obviously you can just add it. And then for every edge, you can keep like at most one cycle. And you just need to keep track of the number of edges in every component and like the connectivity with, for example, disjoint set union. And this way you have like a linear algorithm for, linear multiplied by the constant from disjoint set union algorithm for finding the maximal matching for like any graph that's, how do you say it? Like that has degree at most 2. This is like pretty much the main observation. Like it's used in some problems. Like if you create some basically like a bipartite graph, and you notice that all of the degrees are 2 or at most 2. All right, so I got a question, which is basically if I can explain it with a drawing. Like I can try. So yeah, let's give me a second to just like try explaining it with a drawing. I think I have like some notes here. I apologize for the ugly drawing, but yeah. So, all right, imagine that we had like the left side, which had a bunch of vertices. Okay, so those are like the positions, so that's X. And then like on the right side, we will have like all values. So actually I'm gonna erase one of the nodes so that I have like a simple case. So it's like, from this one we have two edges to those two, for example. Because like in some sense we can just choose we don't really care about the exact values, we just care about the relative order of the sides. Then for this vertex, for example, we have just one edge to this vertex, and then let's say that this one has edges to two vertices, which are like two other vertices, and here like there are some other vertices, but like in general this will be x and this will be y. And I mean, obviously there exists a perfect matching, like we can match those two, then like, and this one, and like basically this one and this one, and then like those two. Or like for the bottom two we can just match any other. And like the thing is that I'm gonna label the nodes now in the y by 1 to 4. So that will be like 1, this will be 2, this will be 3, and this will be 4. And our idea is that we create a new graph which will have like 4 nodes. And yeah, let's say that we have those 4 nodes. I'm just gonna move this thing to the left. All right, so we have those 4 nodes. Yeah, sorry that I'm quite slow with drawing, but yeah. And now let's start going through x. Like x is basically the edges, and let's just try adding every edge. So initially we have x, which has ai equal to 1 and bi equal to 2. So we need to add an edge from 1 to 2. And yeah, we just add it. We can see that this doesn't really create any component with 2 cycles, so we are fine with adding this thing. And yeah, we can just continue to the next x. So the next x is basically like this one, which is connected only to 2. So this means that if it has a single edge, this means that ai is equal to bi, or in other words, we have just an edge from 2 to 2. So it's like a self loop. So we have such an edge. And notice that now we have created a cycle in this graph. So it's like basically this component is now a cycle. I mean, not a cycle, but like it has a cycle. Then we go to the third position, which is like, yeah, the blue thing. And it has ai equal to 3 and bi equal to 4. So we need to add the edge from 3 to 4. And so we add it. And this again doesn't create any cycle. And now let's imagine that we actually had an additional position, which was from, yeah, like it was here, and it added an edge from, again, 1 to 2. So it was like connected to 1 and 2. And this now turns out that now we need to like again add an edge here if we want to have like a matching. However, we already have a cycle in this component, so we can't really add a cycle because like we want to ensure that every component has at most one cycle. And this means that we can't really add this node to our matching because like we already have the components fixed. And this is problematic, mostly because I mean, you can convince yourself that we have no way of matching those 3 vertices which are in the same component, like the first 2 which we had initially, like the 1 to 2 edge, because like we have its direction. Then the second one, which is like the last one, like the one with the double edge to 2, so like the self loop, and finally the like the last one, which is connected again to 1 and 2. So there was like a comment. There is a simpler explanation, I guess. You get a component with n plus 1 edges and n vertices, so you can't match an edge to a vertex. Oh yeah, like this is a pretty good explanation in the comments. One way to actually argue about the whole thing is by Pigeonhole Principle, which is relatively simple. I mean, when you have a component with n plus 1 edges and n vertices, so like, in other words, a tree plus 2 edges which create the cycles, then you have more edges than vertices. And we have this bijection that every vertex is in some sense like something from the right part, and every edge is basically I mean, the edges are basically the edges in our new graph are basically the x vertices. And yeah, because like of Pigeonhole Principle, there will always exist one of the edges will always be unmatched. And yeah, when one of the edges is unmatched, this means that yeah, you don't really have a matching. So that's like a very good observation. And yeah, it basically shows that we have, I mean, like it shows that when we have more than n plus 1 edges, we don't really have a matching. And now the only thing left to do is to show that if we have n edges and n vertices in one component, then we always have a matching. And so that's the case because, like, I mean, the tree case, when we just have like a tree, is quite obvious because, I mean, there's always a way to match all of the edges with some vertex because, like, again, the choice of AI versus BI depends on the direction of the edge. So, like, let's say this direction will mean that we have matched this edge with like AI, and the other direction will mean like we have matched it with BI. And I mean, for tree, it's basically very easy because we have no cycles. And if you choose just one of the leaves and you match it like that, this is the same as just erasing this edge and this leaf. And if we have chosen the other direction, so like if we had chosen the other direction for a tree, so if we have matched it like that, this means that this vertex is discarded. Then we match this edge with this vertex. And this means, like, for all vertices that also have this, for all edges that also have this vertex, we have to choose the opposite direction. So we have to choose the direction like that. And if you had another edge like that, and so on. Or in other words, like, we basically just uniquely determine the direction. So I mean, obviously then for trees, we always have a matching. Then for trees plus 1 cycle, we basically have like this tree, and then we have like a small cycle here. The thing is that if you choose the direction of one of the edges in the cycle, then all other edges will the whole cycle will have to have the same direction. And then we end up with basically the same thing as the tree, which is when you have like one node, which is, I mean, basically like the direction of the cycle should be the same. And then from one vertex, you want the directions to be basically in the same direction, like down the 3 nodes of like this. Yeah, I'm not quite sure how to explain this very well, but I mean, we have like this main cycle, then there are those just nodes that are part of the tree, and like we know that those edges need to have like the direction which is basically down. And yeah, like that's pretty much it. And you can actually, from those 2 observations, you can easily see what's the number of maximal matchings. But like I'm gonna go to it in a second. So yeah, I mean, I hope I did like at least, I mean, I know I didn't explain very well, but like hopefully you got the main idea, and it's that we can basically just maintain whether every connected component has more than 1 cycle. And I mean, if we add an edge and it creates more than 1 cycle, then we don't have a matching. So in some sense, if we just maintain a data structure that keeps our connected components, and also for every component keeps the number of cycles, and makes sure that we always have at most 1 cycle in a component. So in other words, every component will represent a tree plus possibly 1 additional edge or cycle. So yeah, basically, like if we maintain such structures, there is an easy way to check whether whether a perfect matching exists. And if it's basically if this condition of having at most one cycle is true. So yeah, that's pretty much it. And now, I mean, like, the hard part of the problem was to basically implement this thing, because I mean, this trick with degree 2 is quite popular, and I mean, even if you Google it, I'm pretty sure you can find it, because like this problem is pretty famous. And yeah, like there are like a bunch of I mean, you can basically check the editorial. Also, there are some other problems that use this trick of solving matching in graphs of degree 2. And the main observation, as I said, is that every component should be a tree, or a tree with one additional edge. So yeah, now we are only left with the part of to actually see how to implement the whole thing, and also to see how to count the number of maximal matchings, although I said the general idea already. So yeah, basically the first observation is, when counting the number of maximal matchings, is that we can just consider all of the connected components separately, and then just multiply their results to get the number of matchings. And I mean, this is pretty clear, because if two components aren't connected, then we can choose just any matching in the first one, and then any matching in the second one, and the two results are multiplicative. So yeah, you can just multiply the different results. And yeah, now let's see what will happen when we have a tree. So like, the first observation is that if we have a tree, the number of possible matchings is equal to the number of vertices in this tree. And this is pretty neat, because like, again, we use this construction I mentioned with choosing a leaf and then like the edge to it, basically. And we have two options for the direction that goes to this leaf. We can basically just match the edge with the leaf, and this means that we effectively just erase this leaf. And then the second possible outcome is that we basically just match the edge of I mean, basically we match the leaf edge to the other vertex, so not like the leaf, basically like the parent of this leaf. And this effectively just uniquely determines all other edges, or all other directions. So like, if you use induction using like the first rule, like the first rule of choosing the leaf, and we can, just for the sake of the argument, we are always going to choose the leaf with the minimal index, and we are going to consider two options. The first option is basically just match the edge to the leaf, and this just removes this leaf, and we consider inductively the other part of the graph. So this is like, we have basically f of n is equal to f of n minus 1, because we remove this leaf. And then the other option is if we match the edge to the parent of this leaf, and in this case we uniquely determine the whole matching, so this is just an additional one. So we basically just have f of n is equal to 1 plus f of n minus 1, which just gives us that f of n is equal to n, or in other words, the number of matchings for a tree is equal to the number of nodes in this tree. And yeah, that's like the first observation. Basically, when we have a tree, we have the number of its vertices, number of matchings, like if a component is a tree. And then the second case, which is like a tree with an edge, it's way simpler, because like, if we just choose some random edge from the cycle and we choose its direction, then the thing is that there are basically just two ways to choose the direction. I mean, like, you can either have the direction clockwise or counterclockwise on this edge. So in some sense, we just have only two matchings, because if we just choose any of the edges, if you just fix the direction of any of the edges in the cycle, we can uniquely determine everything else. So yeah, that's pretty much it. However, there is like this small problem. Basically, like, there is this case when we have self loops, or in other words, if we have like ai is equal to bi, because then our cycle in our component will be it will basically be a self loop, and actually both of the directions are the same matching. I mean, because we have just a single vertex, so in some sense, like this, if we just choose the direction, like both directions will basically be the same thing, if we have like a self loop. So if our cycle is basically a self loop, then the number of matchings is just one. So yeah, that's like the corner case, which is, I mean, you have to notice it, but it's not very hard because like, yeah. So to recap everything, yeah, like there is just one matching when we have a self loop. So to recap, basically the answer is the product of the component sizes of the three components multiplied by 2 to the number of components that have a cycle, and the cycle isn't a self loop, which is effectively just the number of components that have a cycle, like 2 to the power of the number of components that have a cycle, minus the number of positions such that AI is equal to BI, because like that's the number of components that have a self loop. And yeah, now we basically just have to see how we can handle all of this with a linked tree. And yeah, that's like the complicated part of this problem, because it's not the trivial linked tree, as we need to also handle this size. Like normally when you implement linked tree, you can do almost all tree problems with it. Like there are some things you can't really do, but like you can do quite a lot of things with linked trees. But something quite annoying about them is that if you want to handle some subtree information, most of the times it's slightly tedious. In this case, we didn't really need to handle subtree information for linked trees, but we had to count the number of elements in a component. And this turns out to be not so easy. And now I'm going to try explaining it. But first, let's go to the basics of linked tree. So yeah, actually before that, basically here I have added some notes, which is what we need to have for our linked tree, which is our structure. Every component, we basically need to keep track which components have a cycle, which can be done that as in linked tree, every connected component is always a tree. So basically, as we also want to handle components that have a single cycle, for every tree we are gonna keep a flag or like an additional edge which will represent the cycle. Like if there is no cycle, this will simply be none or something like that. And also we want to maintain, as I said, the size of the connected components, and this isn't that easy. But yeah, like let's first start with linked trees. I'm gonna explain the general idea, and I'm also gonna implement them with trees. A good thing here to note is that if you implement linked trees with trees, the complexity turns out to be log squared per, like n log squared amortized. However, in reality, the constant is very low, so this performs pretty much the same way as the splay tree. I mean, maybe if you implement splay trees very well, you can see a difference, but like in the past I have tried like benchmarking both of the implementations with trees and splay trees, and from my experiments it seemed that both of them perform similarly. So yeah, in some sense, like splay trees, I mean, obviously like the preferred thing to do for linked trees is to use splay trees, but like you can also do it with trees, and in my opinion it's relatively simple because you don't really need to learn the whole thing about rotations and stuff like that about splay trees. Again, splay trees aren't that complicated, but I prefer implementing linkeds with trees because I just find it easier. And yeah, now let's say what's the main idea of the linked trees. So as I said, we are basically, the linked tree will represent a forest of different trees. So basically like we just have a bunch of small trees. And the main idea is that we have this definition of chains, and every chain is basically just a vertical sequence or a vertical path of nodes, such that all of them are represented by a binary search tree with a key equal to the depth of the nodes. This may look slightly weird, but I'm gonna just open the Wikipedia page. Yeah, that's not what I wanted to open, but the Wikipedia page, and I'm gonna go to the picture and I'm gonna show what I mean. So basically, like if we have such a component, what I mean by trees, by chains, is basically like just paths which are like vertical paths. So in some sense, from some ancestor to something in subtree, or like something like that. You can see like the thick edges here, like the black edges. So yeah, basically we have those chains. The first one is basically this thing, then we have this chain, and then this chain, then this chain, and like those vertices which are like alone in their chain. And in some sense, like if you're familiar with heavy light decomposition, it also partitions our structure into chains. But the difference between heavy light and linked is that in the linked tree, we dynamically will change the chains, and this ensures that we'll have a pretty good complexity. Yeah, so basically, you can think that every chain here is basically a binary search tree, where the key is basically the depth of a node. So in some sense, the key for, in some sense, like if this is binary search tree, like this chain from C to M, then the C will be the leftmost node, then the next node would be F, then we'll have K, and then we'll have M. And yeah, I mean, like, basically we have chains like that. And then we have this operation, which is frequently defined as access, which is given for some node. Like, basically it's like, you could, let's say it's given for U. And what this access operation does, like this is the main operation in linked trees, is that it dynamically changes the sequences, or like, basically like the chains. I'm gonna draw a small example now, like in a bit. But what basically access does is that you choose access from some vertex, and we extract the chain from this vertex, like let's say U, to the root of its component. And basically what we have is that we put this, basically like the chain, the whole path in a single chain. So that U will be the last node in the chain, and the root will be the first node. Or in some sense, like, let me just draw some example. Let me first check whether there is one here, but I don't think so. So, yeah. Like, I'm gonna draw the chains in some different colors, but like, imagine that you have, like, this is the chain of the root. Okay, that's large enough. Then you have, all right, so in black, I'm gonna, so all edges that don't, aren't a part of any chain, like this black edges, for example, are called parent pointers, because like in some sense, from the topmost node from some chain, we have like a pointer to some other vertex, which will represent the structure, because like we have a chain, we have a bunch of chains. So yeah, sorry about that. There is like this main part about linked trees, which I forgot to mention, which is like the path pointers. So in some sense, every vertex, like every top vertex in a chain, should somehow keep the information about its parent. And so that's why we have like the path pointers, parent pointers, or like in short PPs. At least like that's how I refer to them, and that's how you can see them in a lot of implementations. So like it comes from like basically just parent pointers. And yeah, we have like a parent pointer for the top of some other chain to some vertex, which is like a node in some other chain. So yeah, let's have like some green chain, because like I first wanted to show what the access does, but like the way we keep information about the structure apart from the chains is basically using those parent pointers. And like for the root, which is like the topmost vertex, the parent pointer is basically just equal to null, because like we have nothing here. So yeah, like that's basically what we have here. And let's just have one additional chain. This structure isn't like the best one I have drawn, but like, yeah, it's a simple graph, I would say. And yeah, like let's have this new chain. And let's say that we are gonna access, yeah, cool. So yeah, let's say that we are gonna access this node. And this means that we want to put the whole chain from this purple node to the root into one new chain. So in some sense, like, we want to get the path from this thing to the overall root and put it into one chain. So what we do is effectively that we are going to just jump using those parent pointers, and we are going to merge and cut some structures, or like some chains. So in this case, so I'm going to copy this whole thing so that after that we could compare what will happen. If we run access on this node, then we are going to get something like that. So we are going to start from the bottom thing, and we are going to basically like cut the pointer here, like the parent pointer, and like the edge below the vertex that the pointer connects to. So it's like this edge. We are gonna create a new chain. So like we basically just cut the green chain into two parts. So that's why we put a parent pointer here. So now like the green chain is two different chains. And what we do is that we basically just need to merge the prefix of the green chain with the suffix of the blue chain. So in some sense, we basically just merge those two chains. So yeah, in some sense, like we had two nodes here, and we merged them into one new chain. And like we keep the new parent pointer for the bottom, like, yeah, because we basically split the green chain into two parts, I'm just gonna again keep the green color here. And now we have like a slightly larger blue chain, so it's like that. And what we do is basically we cut the parent pointer again, now to the red chain here, and we cut the edge below that vertex, so this one, and we just put this thing like that. And now we just also gonna change the color, because yeah, we have a new chain here. So yeah, in some sense we basically just cut the chains and like extract the path from our vertex to the root. And the final thing we need to do is, because we wanted our vertex we did the access to, it was like the purple node here, we wanted this vertex to be the last thing in our chain, and like the first thing will obviously be the root. And to do this, we basically cut the chain after this vertex, because like initially we had this blue thing, and what we do is we also cut this chain, so we have like a parent pointer to this vertex u, so it's like that, and the rest of the chain. So it was like here we had like a single vertex. I'm going to use like a new color for it, because in some sense we cut some suffix of this blue chain, which in this case is just one node, but like effectively if our sample had like some more nodes on the bottom, like that, for example, then what we would have had is basically just like two nodes here. And effectively, that's basically what the access does. We choose some vertex u, and we extract the chain from u to basically the parent. So initially, like the access seems like it seems like a quite useless operation, but it turns out that we can do a lot of different things with access. So yeah, let me show some operations. Imagine that you have like two trees, which are basically like in this form. So it's like some different chains linked with parent pointers, and like we have another component. So yeah, that's like I'm gonna put it slightly below everything, because yeah, it doesn't relate. But like in general, here I just explained what the access does. Access just, you get a node and you just extract the path from this node to the root. And something I forgot to mention is that if you just unite those two binary search trees, because like you need to combine chains, so effectively you need to unite binary search trees. What you can do is basically just I mean, you can see that the depth of everything in the top, in the upper chain has, like everything in the upper chain has like a lower depth than everything in the lower chain. So in some sense, it's like basically this chain will always be to the left of this chain when we consider the binary search tree. So like the unite is basically just a merge of two trees. So that's pretty simple. And like when you want to split something, basically like a chain after some vertex, it's effectively just splitting after a node, because I mean we have this node and we just want to remove everything after it, so we effectively just split a tree. So yeah, like let's go back to what I meant about like the access. Basically what I want to say is that the access is pretty useful because we can do a lot of operations with it. And the first one actually that comes to my mind is we are given a tree. So yeah, like we have some tree here. I'm gonna just write it like that. And we want to handle operations that are basically two vertices, like x and y, and find their LCA. So like we want to find like the LCA z, which is here somewhere. And it turns out that there's a very simple way, which is we, can I actually write text? Yeah, I can. That's pretty cool. Which is like, we first access x, then we access y, and then LCA is equal to basically that. I mean, basically like the LCA of x and y, or like z, is if we first access x, so we basically just built initially a large chain, which is from x to the root, which is here. So this is built like a chain. And then if we access again y, what will happen is that we basically build such a chain, and the red chain is basically cut here, just below the LCA. So basically somewhere here. Then the parent pointer of this chain will basically just point to z. So like that's a way to do LCA, and it's pretty useful. Then let's continue with some other things, like the depth of some vertex, for example. Like for the depth, it's like we have some component and we are interested in some vertex x and its depth in our tree. So the main idea is that we basically just extract this path. So was there some comment? I don't think so. So yeah, we basically first access x, and now you can notice that the depth is equal to the size of the chain of x. So in some sense, like for depth, we have like access of this vertex x, and then our answer, or like the depth, is equal to basically just size, or like the number of vertices in the chain of x. And like this is very easy to handle in for trees, because like you just have an additional variable for every node, which is the size. So yeah, basically that's how you find the depth. And now, like, I mean, basically the name of our structure is linked trees. So in some sense, we need to be able to dynamically erase and add edges. And first I'm going to explain how to do the addition of the edges. So like now if we have like a component, like, yeah, and we want to, actually we have two components. So this is the first one and this is the second one. And we want to add like some node, for example, this one. Yeah, sorry about it. I was just thinking about something. whether there is an easier way to implement it afterwards, but like I'm just gonna implement the standard linked tree, like the one I implemented in the editorial. So yeah, like imagine that we have we want to add an edge from like from the root of some component to some basically some other node over here. And what we do is that, so let's say that we basically want to add this edge from X to Y. The first thing we do is that we are gonna access the root of the second tree. So we access Y, and what this will do is basically we'll have basically a single chain that contains only Y, because like we have accessed the root of some component, because like we have assumed for now that Y is the root of some component. So yeah, basically like what we initially do is that we access Y, then we have like a chain or like a binary search tree with a single node, and what we basically do is that we want to, in a way, like add this chain to the end of the chain for X, and this can be done by an access for X, and like yeah, I mean you access X, and now we basically just merge the chain for X and the chain for Y, and this effectively just adds the edge from X to Y. So the slightly complicated thing is that here Y needs to be at the top of the root, but we can also easily handle this for any node, and this is done by rerouting, which is like the final useful operation with which we can basically handle absolutely everything. So the idea is that we have like an additional operation, which is reroute. So we have like some tree. So this one's for like adding an edge if Y was the root of the tree. So like if we want to make the root of some component the vertex X, it's actually relatively simple, and I'm gonna just write it here, and it's just for the reroute of X is basically defined as an access for X. This extracts the path from X to the basically the root, and what we need to do is we want now X to be the topmost vertex, and it turns out that we can just reverse the chain of X here. So like the reroute is basically just you access the vertex and you just reroute the whole chain from that ends in X. And yeah, this can be easily implemented by lazy for our segment for our trip, with lazy for our trip. And yeah, that's pretty much it. Now if we want to change our addition of like this was defined as the link, so now like if we want our link to be for any X and any Y such that they are in different components, the easiest thing to do is simply to just reroute at Y. Yeah, I can't spell, unfortunately. So yeah, what this will do is we basically just reroute the component of Y so that we ensure that Y is the topmost vertex, then we access Y, then we access X, and we have like this thing. Then we know that X is the bottom thing in its chain, and we know that Y is in a single chain by itself, so we can effectively just merge those chains. So yeah, in some sense, like the chain of Y is a single element right now. And yeah, those are pretty much the operations. The cut now is also very simple. Like imagine that you have like some component, and like somewhere here you have a vertex, and you have like another component here, and you want to cut this edge. So it's like, so this is like X, and this is like Y. The cut is effectively, you have two edges, but you're not sure which one is on top of the other. And like the easiest way, in my opinion, because we already have the reroute implemented, is to just like, so we have like cut of an edge X and Y, where we know that x and y are connected right now, it's simply you actually reroute at x, because like you want x to be the new root. You have no trouble with doing this. If you want to keep the previous information here, you can like have some temporary information about the previous root, and then you can reroute back to like the initial root. But in our problem, we don't really need this thing. So the cut is literally you reroute x. So x is like the top vertex, and then you just access y. So now we have like a trip with exactly 2 nodes, and like you just split middle. Like we have like the chain, and we just split it in the middle because like it has exactly 2 elements. The chain of x or chain of y, both chains are basically the same. And yeah, the final thing you need to do, I mean, basically like the split in the middle won't change the parent pointer. So yeah, that's pretty much what we need to do. We basically just effectively we create a chain with only those 2 vertices, like x and y, and we just split it in the middle, and we don't fix the new parent pointer, and this basically just cuts our structure. So yeah, like those are the main operations, although like we won't really use the access and the depth in our problem, but I mean, it's good to know that all of those operations are possible. It's also interesting that we can do path aggregation or like path queries by simply, if we have a path from two vertices, like if we have some path from x to y that goes basically through some LCA, the way to handle it in link cuts is basically you reroute at one of those vertices, and then you access the other one. And now you have the path from x to y in the chain from x to y. And yeah, the good thing about it is that the chain is in a binary search tree ordered by the priority, basically. And yeah, that's pretty much how link cuts work. And they're very convenient if you have some queries for trees. And yeah, in general, they're a very cool concept. They have a very cool concept. And the only left part we have, like, which is theoretical. After that, we are going to go to the implementation. So there was like a question, maintaining depths of nodes can be completely handled by lazy values in trip nodes. Well, yeah, basically like the depth was in some sense the size of the chain, because like if you access some node, our depth will basically just be like the size of the binary search tree, because like every chain is always a binary search tree. So the way you handle the depth is you simply access some vertex and you just extract the size of this chain, which is like, I mean, you just have like an additional variable. You won't really need a lazy, as you can compute the size as just the sum of the sizes of the 2 children. So there was another question, in the cut operation, can't we access x and set the parent pointer to pointer of y to null? Well, that's effectively what we do, but like we need the reroute mostly because okay, so yeah, this might be, so I mean like we needed the reroute for the link operation, not really for the cut operation. However, an easier way, in my opinion, to do this was to just again use the reroute, because we don't really touch any pointers, and all of our cut operations, like link operations and so on, we'll just use some lower order functions and we won't really touch the structure. And in some sense, like, in my opinion, it's easier to make mistakes if you always touch the pointers and so on. If you just have everything in some functions, which are like that, I mean, it's just like, I guess, a preference of style. But yeah, it's also valid to just, I mean, it's also just valid to access x and just have the parent pointer of y to null. Because like, we know that y will be the top of the chain. So yeah, I mean, it's perfectly valid. You can just not access it. I mean, actually, even I'm gonna rewrite it like that because I actually liked it, because I mean, yeah, it actually looked pretty good. So yeah, first we are gonna access. So yeah, let's actually we first are gonna reroute at y, because we still want to ensure that x is above y, because like else we'll have to have an if here. If x has a larger depth than y, then we just rearrange them. But like we can simply reroute in the beginning, then we can access y, then we can access again x, because so that like we have them in two different chains, and now we can just have that the parent pointer of like chain of y parent pointer is equal to null, because yeah, that's effectively what we do. Probably I'm also gonna implement it like that because it's easier. So okay, so yeah, that's pretty much it. And the only thing, so I actually stopped when to look at the question, but I was gonna say why linked trees are actually fast. So you can notice that it may turn out that one of our operations is actually very slow, because the axis, in some sense, basically just goes through the parent through the parent pointers, and it basically just collapses them and merges some trees. So in some sense, we could have had like a lot of parent pointers like that. Like we've had like a bunch of other parent pointers and so on and so on. And if we had like an axis here below, then we would have had to go linearly through all of the parent pointers. And that's the thing about linked trees. It turns out that even though some of our operations might be slow, the overall, like the amortized complexity would still be n log, or like n log squared if we use trips. But as I said, like trips are relatively fast for linked trees, so I prefer using them, and the implementation is relatively, it's not that hard. So yeah, that's basically the thing. I mean, when you access some node, like below, you have to go through the parent pointers, and this could be linear. But like in reality, the thing is that you can't really construct a test that makes this thing run slower. And if you want to analyze the complexity, you can use the potential method. I'm not gonna explain it here, but there's a very good tutorial by a professor from MIT who actually explained how linked trees work, and he also has a proof why splay trees. Like why the linked trees are fast when we use splay trees. By fast, I mean like faster than log squared. But yeah, that's overall the idea. I mean, basically the axis might be very slow for a particular operation, but in the general case, it's like if you just average out the complexity over all runs, I mean, it's small, because I mean theoretically it will be n log amortized. So yeah, that's pretty much it. And I guess let's try implementing the whole thing. I'm gonna wait for like 1 or 2 minutes before implementing it, so just to see whether there are some questions. If there are none, you can just like write in the chat where there are no questions, so that I won't wait for 2 minutes. But yeah, I tried my best. Maybe like if you're interested, basically because for linked trees we can handle almost all operations. So if you have some questions about how to implement some different operations by using access and reroute, like just access and reroute, you can ask, and like I can explain how to implement the operations now. Because after this point we are going to go back to our problem, and we're going to basically implement like that problem and linked trees. After that I'm going to leave the implementation probably in the chat or somewhere, but like you can also try following along and coding it with me, but if you don't want to, that's also totally fine. So yeah, it seems that there are no questions. I didn't really wait for 2 minutes, but yeah. Let's start implementing this solution. Okay, so it was array create. So, all right, let me just, I'm just quickly checking whether everything can be seen, but yeah, it seems like that's the case. Or actually, I can increase the font size a bit, I guess, even further. Yeah. Okay, so we are going to start by implementing a trip. So for trip, we need like the random generator. So yeah, let's have it here. And now we need like a structure that will keep our nodes. Basically, node will represent a vertex of our tree. So the first thing we need is basically, we need two nodes. The first one will be the left child of, because apart from this being a vertex of our tree, this will also be a vertex of the tree. So it's like both a node of the tree and a vertex in our graph, or like our tree. So we have like those left and right, which are basically the left and right children. Then we have like the parent of some node, which is like the parent in the tree and not the path pointer, not the parent pointer, which is like the pointer to the other chains. So we have like also a PP. As I said, like I'm gonna refer to those parent pointers as PP. So now we also need a size for this subtree, because let me just give me 1 second to think about this. Do we need that? Actually, I don't think we need a size in this problem, because we don't really want to implement the depth. What we need to do is like, so as I said, computing the component. Okay, actually, I'm gonna stop the implementation for a second, because I'll have to go back to the problem for a second. So remember that we needed to count in our problem, we needed to count the component sizes for the three components. And the thing about that is that actually, I mean, those component sizes aren't that easy to implement using linked tree, because it's subtree information, and subtree information is slightly more complicated. And to do this, what the main idea is that every time we have like an additional variable in every node, and it's basically like the component size, or like the number of parent pointers that for like, so for every node, we are gonna keep the sum of the subtree sizes of all other parent pointers. So like for this node, we are basically just gonna keep like the sizes of the components of everything else that shows as a parent pointer to this node. And then in the axis, whenever we change a parent pointer, we're gonna just decrement the value in this node with the rest of the chain, like basically this value. I mean, it's slightly complicated, but it's doable. And every time we change the parent pointer, like the PP, we need to also change the subtree size for this node. And then like the component size will just be the subtree size of the whole thing. But yeah, we have like this component size. Yeah, let's just call it component size. Then we have also the so count PP will basically be the sum of the component sizes of the parent pointers. That's like basically the variable I was trying to explain. And yeah, we also need the priority for our trip. So yeah, let's just create the default constructor, which is construction, which is like, we just have null pointer, and then the component size is equal to count is equal to priority to 0. Although like we won't really use this constructor, but like, yeah. I mean, actually, let's just use this one, and I'm not gonna have another one. So when we have like a new node, what we do is we have like left, right, the parent and the pp are all equal to no pointer in the beginning, then the component size is equal to basically 1 because we have like a single node. Then the priority is equal to random, and then like the count pp is equal to 0 initially because we have like just create a new node and nothing actually points to it. In some sense, like this will be similar to reference count, but not really. It will be like, I mean, it will be similar to the reference count, but not really. Yeah, the perfect way of me to explain this, but okay, so now we need like, let's just have some utility functions which are like component size. This will basically just return, and it's given for some node. Okay, so also I'm gonna, by p node, I'm gonna basically represent a pointer, so I'll have like a type def here, which is basically p node will be a pointer, and everything here, oops. So everything will be defined for p nodes because like we have pointer to some nodes. And so the component size is basically if t is not null, so if t exists, then we return the component size, else it's 0. It's like just a simple function. Now let's implement the pull for our trip. So we have like some node t, and what we want to do is basically if t doesn't exist, then we just return. Otherwise we push the left child of t and we push the right child of t. So now we also, this means that we'll have to implement the function push, which for some vertex basically just pushes the lazy. So if t doesn't exist, we just don't do anything. And we actually need the lazy for the reversal, because like, yeah, we had like the reroute which required reversing something, and so we will also have like a flag. Let's just have it as a boolean, and here the reversal will be equal to 0 because, I mean, yeah, basically like initially we don't want to have a lazy. So the idea here is basically like if t.reversal, then t.reversal is equal to 0. Basically this means that we want to reverse our subsegment, which can be easily done by just if the left child exists, then we just propagate the lazy, so XOR it with 1. If the right child exists, then we propagate the right child's lazy, and finally we simply just swap the two children, because like that's effectively a reverse. So yeah, we just implemented the reverse. Now when we pull some node, we want to ensure that the left node is fixed and the right node is fixed. And the other thing we want to ensure is that basically like, actually I'm gonna implement it simply as like the component size of t is equal to 1 because like we have the current node, plus basically the component size of the left child plus the component size of the right child, and finally plus this final thing, which is I mean, I had it in this variable, which was count pp. So it's like plus t count pp. So that's how we fix the component size. We have the pushes just to ensure that like the two other things are pushed. And finally, now we need to actually propagate the pp and the parent and the parents. So like we have those two pointers, which are initially null, which are parent and the parent pointer. The parent actually corresponds to the parent in the tree and not the in the trip and not the actual tree, and the parent pointer is defined only for the top of the chain. However, I'm gonna keep the parent pointer in the root of every chain. So in some sense, like when we have a trip, which is like the binary search tree, I'm gonna keep the pp only for the root of this trip, and to know that the root won't always be like the topmost chain, the topmost vertex in the chain. It may be just some random vertex, which turns out to be the root of our trip. But like it's easier to implement it like that because if you just keep the parent pointer for a single node in our trip, the most convenient thing would be to just keep it for the root of the trip. All right, so okay, so what we do is basically if the last, so first I'm gonna fix just the parent nodes. So the parents are like the parents in the trip. So if like the left node exists, we can just fix the parent of the left child to be just t, because like just to ensure, like from the pool. And if the right child exists, we just ensure that the parent of the right child is basically just p. This is in the trip. And now it's basically like the parent pointer. What we do is basically if the left child exists and the parent pointer is in it, then what we can do is basically we can just extract the parent pointer from it. So in some sense, like if the parent pointer was in the left subtree and like the left child actually exists, then we just extract it, and then we just like after extracting it, we need to like make it equal to null, because like we basically just remove it. And then we have like the second case, which is if the parent pointer was in the right node, then what we do is basically we have like we basically do the same thing, but for the right node. I could have copied the I could have copied the whole thing, but yeah, that's also fine. So yeah, we just extracted everything, and like that's our pull and that's our push. And now let's just implement the merge and split for the trip. So we have like a merge. We are gonna merge into a node t, and we have like two nodes which are left and right. So initially we push left and right just to ensure that the information is correct. So the first case is basically okay, so the first case is if left doesn't exist, so then we know that t will simply be equal to right, and we return. Then the second case is if right doesn't exist, then we know that the t, which is like the result after the merge, would simply be right, will be simply be left. And I mean, here what we have is basically like, I mean, now we have like two trips and we want to choose one of the roots. So let's just choose the one with the larger priority. So it's if like the left priority is greater than the right priority, then we are gonna just have we're just gonna merge. So like we have the left priority greater than the right priority. This means that we need to, like, left will be the new root, so we need merge into the left.r. We merge, and there we are gonna merge. So we go to left.right, and here we merge left.right, which is like the left part, and right is the right part, and then we just let's set t is equal, which is the result, to L. And otherwise what we do is basically, yeah, I'm gonna open some brackets here so that it's more readable, although right now it's not that readable, and I apologize for that. And in this case we basically merge into right.left, which is like just the equivalent case. So here it's right.left, and then we have just t is equal to right. And finally we just pull t just to ensure that everything is computed correctly. So yeah, that's basically the merge. Let's think what we are gonna actually need apart from the merge. So we are gonna need a split, and actually the split should. Okay, so I just realized that we need some additional information for the trip. We actually need the depth of the nodes, and this is because in the access we want to. So yeah, I'm gonna go to the nodes now, and as you remember that in the axis for, yeah, this is like kind of an ugly example now, but like when we did the axis here for the whole thing until u, we had to cut our chain after u. So like we had to cut this part out. So that's why we in a way need to split after the position of u to create like a new chain which will be below. And to do this, we actually need to somehow be able to split based on sizes, because like we can easily find, in a way, like we want to find the depth of u and split after this depth, because like that's like a prefix of u. And that's why we also need number of nodes in the current subtree of the trip. So we need also like some size information. So like this size, which is just sz, is the size in the trip and not like the other size. I'm gonna leave a comment here, which is like size in the trip. And let's also have like an just a utility function which will just return the size without like with checking for the pointer not being null. So if like t exists, it's just like the size, otherwise it's just 0. So we have like those two functions, and now what we do is basically in the pool we also want to update the size. So we have like size is equal to 1 plus size of the left child plus the right child. And okay, now let's just implement the split, because we can now implement the split basically. So the split is defined for some node t, and we want to split into left and into right, where we also have some k, which is basically the size on which we split. And so the first thing is if t is, no, the first thing is actually we push t just to ensure that everything is fine with it. And what we have here is basically if t doesn't exist, then left will be equal to right and it will be equal to null pointer, because I mean if we have a null node, then everything, I mean, yeah, like if we have a null node, then both parts will also obviously be equal to null. And now here the if is if. Alright, yeah, I haven't actually implemented the trip in a while. I realized this just now. So let's find the index, which is the index of the root, and it's equal to the size of the left part. Yeah, let's just keep 0 indexes for everything. Like the index is just the size of not left, but like t dot left, because it's basically the number of nodes on the left side. And what we want is basically if index is less than or equal to k. So this means that the root should be in left, because like I'm doing everything inclusively until position number k to be in the left part, and the right part will be everything after position k, excluding k. So in this case, what we do is basically we split, I mean, we actually want to split the right part into two things. The first thing will be, yeah, just give me a second to figure this out. Okay, so we have t, we know that t will be in the root, and we want to split it into t dot right, because like t will be the new left, and then right, because like we know that right won't have anything from t dot left. And then what we can do is that left is just equal to t. Okay, just, yeah, this is just a minor trick to have this on the same line. And also here the k should actually decrease by index -1. It's -1 because we also have the root. So yeah, actually should it be -1 or should it be 0? Yeah, it should be -1, because we want to also have the case where the right part will be like to have t dot r equal to null. And in the other case, we know that index is in the like the root in the other case is basically in the right part. So this means that we can basically just split the left part of the current tree into left and t dot left, and the k won't really change because we go to the left part, and in this case we just have like t is equal to, like not left but like right is equal to t. And just to ensure everything is okay, we pull t here. And now we have a trip which also has like this additional information about parent pointers and so on. And now let's actually start with the interesting part, which is our link cut tree. So what we are gonna need is the following. So let's have the parent the pointers to the nodes, or like I'm gonna have like a large array of pointers which will be the vertices. Let's have like the initialize, like let's initialize n nodes, and the indexation will be from, let's say, from 0. So we have like, we basically just have like the vertex at position, the vertex for I will be a new node, because that's basically what we create. Initially everything is alone, so yeah, that's like basically the beginning. And all of our information for all vertices will be kept as nodes. And now what we have is basically the first operation, which is the access. So let's implement the access for some node t. Okay, so just to ensure that the indentation is the same here, although like it gives, you know what, I'm not gonna bother with it. Okay, it's fine like that. So what the access did was basically we wanted to extract the path from t to like the root, and it, in some sense it should look okay. So the first thing is that t isn't necessarily the root of the chain. So let's have like a new node which is the chain root, which is basically like the trip root of t. And let's implement this function, which is trip root for some node t. And the trip root, what basically the trip root does is while we have a parent, we just go to t.parent. Like we make t equal to t.parent, and we also ensure to pull here, like t, and also like here. And not pull, but we want to push t here and also here. Because, yeah, I mean, although this push isn't really necessary. I mean, actually, you know what? I'm just gonna remove it here because the t.parent doesn't really change anything. We just move t to the, yeah, we basically just move t to the parent until we have no parent, and yeah, in the end we just return it. So yeah, let's have like this chain root, and what we want is actually, okay, now we want to split after, basically we want to split the chain after the chain of t after t, because like we wanted, instead of what I was explaining, let's first remove the right part of the chain, so that like, I mean, we have some chain and we want to remove everything from it after t. So basically I'm gonna create some function which is called remove right for some t, which is basically splits the chain into two parts after the node t. And what will happen here is basically alright, what we have is we need the position of t, which is initially the size of t.left. So in some sense, let's build the position of t, because I mean, like right now we have a trip and we want to basically split it after the position of t. So in some sense we need to find the position, and we also want to find the root. Although I do have the function here, which is the trip root, I can also because I need to find the position, I'm also gonna compute the root. So we have like this ARCRT thing, which is basically the root. And what I'm gonna do is while ARCRT.parent. Okay, also here something that we have to notice. I mean, computing this isn't like the most trivial thing, but it's also not that hard. So, I mean, we want to find the position of t in its trip. So, the first thing to check is whether the reverse thing for the current node, so RT, is actually equal to 1. Because if it is, then this means that we need to reverse this whole segment. And this means that our position is computed wrongly. So what we do is basically the position will be equal to the size of the whole thing. So it's like the size of RT minus the position minus 1. So it's basically just the opposite position. And what we basically do is the following. Until we have a parent, we want to check whether we come from left or... So we have like, we go from the t node up to the root, and at every point we can either... I mean, we have two cases. The first one is we basically come from the left child. The second one is if we come from the right child. And to check this, we can simply do like if rt.parent right is equal to the current root. This means that we come from the right child, and this means that our position should increase with the size of the root and like the left child plus 1, because like the root is also before the current position. And also we have to do the same check if basically if the parent for the root had its reverse flag is equal to 0, we need to inverse our position like that. And finally we just do like rt is equal to rt.parent. And now what we have is the position on which we need to split based on the root, and also what we have is the root, which is like rt. And we want to split after t, so what we have is basically, so let's first extract the parent pointer, so it's like pp, which is rt.pp, and we also set like the parent pointer to null pointer, and yeah, also let's have like the left and right subparts. And what we are going to do is we are going to split the root into into the left part, the right part, and then we are going to split it by position, because like that's the position of t. And that's pretty much it. And now what we have, basically like left is our the chain of t, and right will be the other chain. So the parent pointer of left, we can ensure, so we know that L isn't, so yeah, let's assert that L isn't equal to null pointer, because we know that T is in L right now, so like L.pp is equal to basically L.pp would be equal to the pp, which we extracted here. So the thing, we are actually extracting the parent pointer here because it's defined for the root, and we don't want to mess it up during the split. So yeah, we extract it up here, then we set it to 0, to null initially, and then we just set it again in the chain for left. And similarly, we basically just do, I mean, we have, if the right part exists, because like it may happen that t was the last vertex in our chain, and in this case, we basically just set right that parent pointer equal to basically t, because I mean the parent is basically t. And finally, let's have this function just return the root of our new chain, which is in this case left. So here actually the chain root will be equal to remove right or remove after. Actually, I'm going to rename this function. So it's like remove after this node t, and this basically removes everything after t. And what we do here is basically just while chain root that parent pointer. So what we do is let's have the parent chain, which is basically equal to chain root that parent pointer. However, we again need to remove everything after this, because like we split that chain into two parts. And here what we do is basically just now we just want to, I mean, here we want to merge power chain and chain root. I think this can be easily done by simply setting the chain root parent pointer to null, because like this was our chain, and then we can just merge into the chain root, because like this will be, I mean, this will be the new variable in which we are going to keep the root, and like the left part is basically just the parent chain. Okay, also we need to first extract, so let's extract the parent pointer as from the parent chain. So basically here we extract the parent pointer of that chain. Oops, and here it should, yeah, okay. And also like the parent chain, parent pointer is null. So like both of those are null, and we merge the chain root, the parent chain, and yeah, that's pretty much it. Like the top thing is the parent chain, the other thing is like the chain root. So yeah, we merge those two. Oh yeah, and finally, because like we have the parent pointer, we want to set it back to like the chain root. So that's pretty much the access, and yeah, it just uses like those functions. Something that I haven't implemented here is actually the computing of this reference counter, which is basically the component size. So we have like this count pp, which we need to change in the basically in the remove after function. So the thing about it is that when we do the remove after, what happens is that, okay, so basically we split our thing and we set this new parent pointer. So what we need to do is basically, okay, just give me a second so that I can think it over. Here we need to set the, so it's like, all right, yeah, it's for t, and the count pp for t should be equal to, okay, yeah. Yeah, we should increase this thing by the size of the right component. Like not the size, but like by the component size of the right component. It's slightly tricky. I mean, it's not the easiest thing, but still, it's also not that hard. Like the thing is that we simply need to increment the count of PPs to this thing, because like we create a new parent pointer here. So that's like the first thing, and I suppose we need to do something in the merge, if I'm not mistaken. Yeah, because like we need to decrement something here. So basically we have like the yeah, we should basically, what we need to do is so the remove after should handle everything, if I'm not mistaken, because it fixes the size. But here in the merge, what we do is, all right, yeah. So what we have is that, I mean, we still do have the, yeah, we have like the chain root. So we set this thing here, like the chain root, that parent pointer. However, we also need to, what we need to do is we need to decrement the chain root that parent pointer, which is like the node in the parent chain. So this thing that the count pp should be decremented by the component size, which is like the subtree size of basically the chain root, like the bottom chain. And if I'm not mistaken, that's pretty much everything, because like here we erase one basically like one parent pointer, and in the other case above we just created a new one. And one additional thing we need to do is basically let's like have a function which is pull up for some node t, and what this will do is like while we have a parent, it will go to the parent and it will update the component size. And obviously this thing will be logarithmic because the depth of the trip is logarithmic. So I'll have like this function, which basically this thing. So it's like, and we set t to t.parent so that we can move up. Okay, so yeah, okay, and there are no warnings. So yeah, that's pretty much the access, and now we can actually start with implementing the different operations. So we already have the init, so let's have like the link for int left and int right. And what this will actually do is, so actually those are the wrappers. First I'm going to implement the actual operators. So we have like a void link for two nodes and like a node u and a node v, and what we do is basically we access u, we access v, and okay, yeah, we also need the reroute first. That's why I kind of got distracted. So we have a reroute, some node u, and what we have, what we do is basically we access this node u, and then we have like u dot. So actually, let the access return the new root of the chain. So like in the end, we know that the chain root will be in chain root. So let's just return it because it's useful in general. So let's just have like root is equal to access of u, and root dot reverse is equal to 1, because we basically just reverse the whole thing. And now, I mean, let's just push the root. It's not really necessary, but let's just have a push there. And yeah, the link now is basically just reroute of u. Just to ensure, let's also access u, although this is useless, but I mean, it doesn't hurt having it there, because I mean, in the reroute we basically just access u, so we ensure that it will be the top thing of the chain. But like, let's just access it twice, then let's access v, and now what we need to do is basically let's do the thing with the parent pointer, because like what we can easily do, we know that the v is the top of its chain. Okay, so let's have like some node root v, which is like the thing for v, which is like the root of the chain. And what we have is basically we can set the think of a nice way to implement it, because like I started without having functions for everything, but yeah, basically what we have here is like we want to link v as the child of u. So oh wait, actually the other way around. So yeah, fair. Okay, so let's have like p-node root u, which is like the axis of u. So now we have a single component which is u. I mean, actually, like u is the root. So this thing, like we know that U is the root of the tree, because like the chain is just a single node here. And what we have here is like, if I mean, we want to set basically the parent pointer of U, because it's the root of everything, to be equal to V. And something we need to do is we need to access V, because like whenever we touch, and so that the analysis of the trees, actually of linked trees works, we need to access always. I mean, even though in this case it doesn't really matter whether we access V or not, but it's good to access everything whenever we touch it, so that the complexity is fast. And yeah, so we basically access U, we access V here, we set the parent pointer to V, and what we need to finally do is basically the V that count pp should be incremented by the component size of U. Yeah, basically, because yeah. And now what we need to do is basically, so yeah, we have accessed V, so V is the root. Now what we need to do is we need to pull up from V, and we also, everything here, everything everywhere else where we change those, we needed to actually do a pull up for the chain root pp, because I mean we changed it and we never actually updated it in the tree. So yeah, that's pretty much it here. Oh, and also we need to pull up here. We need to pull up from T, because we also need to update the component sizes in the T. Okay, so yeah, I think that's the link. Now let's have the cut from node U to node V. So we access, actually we reroute at U, then we access at V. Now we have like two things. Now we can access again from U. Now we have them in two different components, and what we can do is basically just T that count pp minus equal component size. Actually, like U is the root, so U that count pp, because U is also the root of its strip because of this axis here. U that count pp will be decremented by the component size of V. And the second thing we need to do is basically, so yeah, we decrement it, and now we need to pull up from U. And something else, if I'm not mistaken. All right, yeah, we also need to change the so V is also alone right now, so we need to also change like the V that pp should be equal to null pointer, because like we just cut this edge, so we need to remove the, I mean, we basically need to remove it too. Okay, so if I'm not mistaken, this should be it for the link and the cut. So we have the reroute, and do I need actually something else? All right, I need the function which would be like component root, which is just simply basically like the root definition of disjoint set union, but like for linked trees. So it's like we have a U here, and it's simply, yeah, we can just access U and just return tree root of U. Oh no, actually it's even easier. You can just return access of U. Wow, I mean, actually I just realized that the root is simply the access of some node, so we don't really need such a function. Okay, what do we need? I mean, I think those are sort of like the functions we need for nodes, and now everything else can be implemented as wrappers. So like the link from left to right is simply, we just link from the vertex for left to the vertex for right. Now the cut from, actually it's, I don't like L and R, so I'm gonna use X and Y. so then we have like the cut from X to Y, so it's just like the cut between vertices X and the vertex for Y. Then we have like the, we have the link, the cut, and what else do we need? We need like root, which would be like the equivalent of the component root, as I said, for some vertex X, and we are just gonna return the access. Alright, so I just realized that I'm gonna need something else, which is inside of the node, and it's the ID for some vertex. So it's like, yeah, we're gonna have an ID, and here in the when constructing a node, so here I'm gonna have an I, and let's also have like an empty constructor, which is just gonna fill with stuff from the stack or the heap, depending. And like we are also gonna have an ID, which is like the ID of the vertex. So we have like the ID is equal to I. So yeah, when we create a node, we create it for the specific ID. And yeah, what's the root is basically we just access the vertex for X. This returns the root of the new chain, and yeah, then we can just return the ID. And then like we need the component size, however for a linked tree, not like the generic component size. For some vertex X, it should just return the basically should just do the same as the previous function. We like access the current vertex, but then we just return the like the main component size function. And I think those are the functions we needed. Yeah, it's good that it's failing though. Oh yeah, now because like you know what, I'm just gonna rename this function because I don't like component size. How should I rename it though? And I'm just, yeah, here it should be comp size, but like the wrapper function will be just component size. Okay, is it failing? It seems to not be failing. So that's a good sign. This means that we have already implemented all of the functions we need, and now what we have to do is basically to implement the problem. Okay, so did it have tests? And let me just open the problem statement. First, I'm gonna just implement it for finding the size of the matching for every position. So like in some sense, we are just gonna maintain whether every component is. I'm just gonna keep like the matching of the whole thing, just to check whether the functionality works. So okay, so in this problem we are given, oh no, we have tests, which is kind of unfortunate. So yeah, let's have the tests here. So okay, so we have n, we have like the A array, the B array. We input n, then we input the array. Okay, and let's also have like the linked tree. I'm gonna just name it linked tree here, and we want to initialize. No, actually before that, let's have like a vector int sorted, which will contain all A's and B's. We are basically gonna compress everything, so we have like yeah, we basically just erase the repeated elements. And now we know that, so the thing is that we wanted to have, yeah, here we need to have an n. Oh, and it's with J. Yeah, cool. So now basically the linked tree should have I mean, let's just first compress the elements. So we have like AI is equal to lower bound of everything in sorted. Let's find AI and let's just find its position. And the same for BI. So now like the size is basically just 2n at most for sorted, and let's initialize the linked tree with the size of sorted. So it will have like as many nodes as values that appear in both A and B. In either A or B actually. So now let's actually solve this problem. So for every position we wanted to compute let's denote the maximum possible of Li such that for some good sections it is by Mi. So just to be sure, okay, so for every position actually we needed to find the next position that is I mean, yeah, basically we need to keep like, we go, if we have like the left border, which will be from left to n, because like n is technically the number of edges and we need to add them one by one. What we have to do is basically, I mean, L is the number of edges, so yeah, let's also keep R, which will be like the right border, and we have something like while we can match the right border, we increment the right border by 1. This seems good enough. And now the final part is basically the head function, which it will be like the match function. So we have like a match function, which is basically for some position I. So okay, we want to update, so it will be a Boolean function, and yeah, okay, so we have an edge from AI to BI, so it's like an edge from X to Y. So let's find in the linked tree the root of AI and the root of BI. Linked tree dot root of BI. So the first case also, we would need an additional thing, which is like, we'll have an array, which is additional edge for every component. So it will be like the additional edge, and initially every vertex is by itself in every component. So here we have like, I mean, we need to iterate over everything in sorted. So we have a loop through everything in sorted, and we said that the additional edge for this vertex will be -1 initially, because like initially everything is in a component by itself, and there are like no cycles. So the additional edge, like added to the tree, will be -1. And yeah, like the first case, if like the additional edge of X is not equal to -1, and the additional edge for Y is not equal to -1, this means that we have an additional edge in both components X and Y. This also covers the case when X and Y are the same thing. So if that's the case, we can't really add the edge from X to Y. So not from X to Y, but like from AI to BI. So we just return false in this case, because we can't do anything here. In the other case, we have actually two cases. The first one is basically X and Y are in the same component, and the second case is that X and Y are in different components. So yeah, like let's first handle the case of X is equal to Y. If that's indeed the case, what we need to check is, so here we can assert that the additional edge of X is not equal to -1. This is because basically if x is equal to y and the additional x is not equal to we can assert that the additional edge for x here is -1 because of the previous if. So like we would have had x here and x here, and this if would have returned. So yeah, we can do this assertion here, and yeah, in this case what we basically do is we just add this additional edge to be I, and we can just return true because we were able to match it. And okay, so that's fine. Now what we need to do is basically just the last case, which is, I mean, we can just assert that x is not equal to y. So this means that we can basically just unite using this edge. So we can just have like linked tree that's basically just link AI and BI, because we know that the two things are in different components. Oh, actually before that, because the link can actually change the root of the whole structure, let's first extract the additional edges. So it's like E1 is like the additional edge of x, and E2 is the additional edge of y. We know that it's either, so actually let's have additional edge, which is basically if the additional edge for x is not equal to -1, then it will be the additional edge for x, otherwise it will be the additional edge for y. Because like we know that it will be either the first one or the second one because of the initial if over there. So yeah. The additional edge for x will be equal to -1 in this case, and the additional edge for y will be equal to -1, and then we are gonna place back the additional edge for the linked tree, that root of basically AI after we have united this thing, and this additional edge would be equal to basically the add e, which we extracted in the beginning. And I think that's pretty much the add. Now this will basically just move the right border until we have something that we can't match. This should handle like the cycles and everything. And now let's actually do the removal of the edges, because like, we have failed here. So here I'm gonna just print a debugging cout, which is like for every position it will be like the right border, like the rightmost border that's valid. And here what we need to do is to actually remove back our edge. We need to basically remove the left edge, like basically A left, A, B left as an edge. So let's consider the cases now. We know that the whole thing is connected, so one way to do this is, there's actually a neat way to do this. So let's have the root. It's basically like the linked tree, that root of AL, just to find the current component. And if the additional edge of the root, I'm just actually gonna use R for the root, actually RT, because root is the function, although it's not a problem, but still. So if the additional edge for the current component is equal to the edge we want to remove, so left, the simple way to remove it is to just set the additional edge to -1, and we are basically fine, because like we know that the leftmost edge seems to be like the additional edge in our component, and like in this case we can just set the additional edge of RT as -1, and we can just continue. Otherwise, what we need to do is we actually know that the L edge is in the tree, so we will have to cut our tree. So what we do is basically so like what we are gonna do is basically we need to, so add E is basically the new edge, like the one that created the cycle, and it's basically like the additional edge for RT. And yeah, okay, so we set now the additional edge of RT to be equal to -1, because like in some sense we are gonna remove this additional edge and we are gonna place it back now, because we know that this additional edge is after L. And now what we do is we basically cut, like, we cut the linked tree from A left to B left, and yeah, that's pretty much it. Like, we basically cut the tree from A left to B left. And now what we can do, so we have like this edge we need to add. And yeah, what we can just do is we can assert that the match of when adding the additional edge E is equal to true. Because like the neat way to actually implement this is that we're gonna match once again this additional edge. Because there are two cases. The first one is that this edge will still create a cycle, like the additional one, and then like the match will handle it. And the other case is that the additional edge will just connect to things, so then the match will be again true. But like in general, after we remove this edge, we can definitely match ADI again. So if I'm not mistaken, this should work, but also maybe I'm gonna be debugging here for a while now, because yeah. Let's just get this test, like one test, which is the first one. Hopefully it's okay. Oh, okay, yeah. So the thing is that here I had a very small mistake, which was that I'm just incrementing right as much as I want, but I need to have like the constraint that right should be less than n and the match of R. So like that was a small problem. Okay, so I also need to write the number of tests. And it crashes, which isn't a good sign. Okay, so let's see where it crashes actually. So yeah, there was like a question, which is any blog tutorial or template code for linked tree. So I mean, yeah, I'm just gonna quickly stop the implementation. I'm gonna find the bug in a bit. So yeah, I mean, you can check the Wikipedia page and also like this Codeforces blog. I mean, it has a general explanation how linked trees work, but wait, there was also like, when I learned linked trees, it was from this MIT class. So it's like, let me check whether the comment is, yeah, it was pretty much this thing, but there's also like a video version of this thing. Like, yeah, it's basically those lectures. And yeah, I advise you check them out. They're pretty good if you didn't get like the idea of the linked tree. But yeah, I mean, this is a very good, like the MIT lectures are very good for linked trees. And now going back to the problem, let's find actually why it breaks, or actually where it breaks. So yeah, let's just have a debugging stop here to see whether we actually get until the initialization. And okay, we do. So it doesn't crash until this point. So let's see whether we actually print at least once. So it seems that okay, so let's actually check whether we can do the root or like the access, or that's like the broken part. So it seems that initially, so we have like the current position, and for it we have like AI and BI. Was this the case? Oh yeah, they are the same. Okay. So actually, let's see what will happen if we just print a bunch of information to see after which addition the whole thing crashes. So it seems that it crashes when we are adding Or actually, is it the addition or is it the cut? Let's see actually if it comes here, because like we also have a cut here, and maybe it will actually crash there. So if the last print is followed by a here, oops, yeah, I copied something wrong. So I mean, it's not followed by a here, so I mean, it should be crashing in the addition. So let's see what happens actually. So we have 2, which is the second edge, well, actually the third one, because we have 0 indexation. So we have this one from 3 to 4. The problem here is, wait, what happens? We have 1 and 2 as roots. Okay, that's fair. And we can't really add, I think. So let's check this part, which is basically the addition. So we have AI and BI. And actually let's print their components, which are like linked tree.root of AI and linked tree.root of BI. Although that's the same information as above, I'm just wanting to make sure that there is no undefined behavior until this point. So let's see whether those will be what I expect them to. I mean, it's weird that we actually don't even reach this point. So that's something I didn't expect. Oh yeah, that's because we don't have a flush here. And I'm using... okay, it's not because of that, so that's weird. Does it even come here? Or here? Or here? Also, the thing is actually that we should go into the false, not the true. Yeah, I just realized that in this case, that's interesting, because like let's find the additional edge for X and the additional edge for Y. So it seems that we are creating a cycle because our reaction. So we have 2 and 2, which is like 0, 0 initially. So yeah, it's here. And here we created an additional edge, or like a small self loop. Then after that, we are adding something from 0 to 1. So like this large component basically has a self loop, or like 1 cycle. So that's fine. And then we are uniting 3 and 4, which is 2 and 3. So it's crashing here, I think. But like, this shouldn't be crashing, like actually here. This shouldn't be crashing, so... Oh, wait. Does it... Wait, where does it even go? Like, obviously it doesn't go into this false. So does it go here? Yeah, sorry about this debugging. I mean, in general, it's not the easiest structure, and yeah. Okay, so okay, the thing is that it doesn't really go there. We are here at position I. Okay, so we are here at 2 where it crashes actually. Okay, that's at least good to know. So I think that's even... So we actually not 2, we should have I here, this will be like 1 the first time. This will be like the same. Actually, this is like the first time. This is the second time. And let's find the first time. Okay, so we are here. So it comes to this point. That's a good thing to know. And I suppose actually the link will be the problem. So we'll need to have 2 frees in the end, but we have only 1. Like, yeah. All right, so at least we figured out that the link is wrong. So let's see why it's wrong. Okay, so so we have, let's see, let's just have a C out here. I actually have a suspicion why it's wrong, so let me just check. So actually I don't know, it shouldn't be that. So yeah, I forgot the flush. Yeah, that's indeed the input I wanted. So let's check this thing again. So it seems that maybe the reroute is the problem, because I'm not quite sure yet. Oh yeah, it seems that the reroute was actually the problem. Okay, so because the reroute seems to be the problem, what we can do is basically reverse. That's weird. Oh wait. Although this is weird, this means that our access has some problem, but if this doesn't crash, then, well, it still crashes. This is at least good. I mean, not that good, but like here. Okay, yeah, this means that we don't reach this point, but we definitely reach this one. Yeah, like we have 1 here, but we don't have the second one. So this means that we basically have messed up the access somewhere. Okay, let's check it out. So while we have, actually a very good thing would have been, let me actually see what the accesses show. Okay, so remove after. What does remove after do? So it should split the chain into 2 parts after the node T. So we have like the position. The position is initially T dot left. So what we do is actually maybe this function is the problem. Let's see, where would we actually reach? So initially we should enter this, like most definitely, so we should have the 1. So after that, let's see whether after extracting the parent we can even get here. And yeah, that's pretty much it. Alright, so actually, yeah, we'll always have yeah, our parent, yeah, okay, this should be correct. Okay. So yeah, let's have this as 4. Let's just simply compile it and see whether at which point this crashes. That's interesting. Because it actually doesn't crash in this function. So this one actually seems to be correct. which is good because because this is like the hardest function in the code right now. So yeah, okay. So let's see. I mean, we have the remove after, which basically removes after everything. This is correct, which is good. So now I suppose that's oh wait, actually it may turn out that, so while we have a parent pointer, so here we have a parent chain. So let's actually have a debugging out just in case. Thanks guys, even though it's not working out. Thanks for at least watching. The moral support is important. I mean, maybe someone who has implemented this thing a lot of times could have already spotted where I broke it, but yeah, to be completely fair, even after when I was implementing this problem, I had like some trouble with the whole thing. And yeah, like at least, I mean, this is a problem from a long challenge. I also tried not using a template during the video, so yeah, maybe I should have, but yeah, it's too late now. All right, so yeah, here I wanted just to ensure that the parent chain is null, so yeah, that's fine. Okay, so, oh wait. And here I found the problem. So it's actually a very stupid bug. So you can notice that here I'm extracting the PP from the parent chain. Wait, actually, never mind. Yeah, that's annoying. I thought that this was the problem, but it's not. Sad reacts. Let's actually see whether we actually reach this point. So it's like that. Okay, so it doesn't reach here. That's interesting. Let's have here 3 here. And here 2 here. So it seems that the component size actually is broken, or let's check the component size then. Although it does have the check whether, yeah, it only does it if the t is not null, so that should be fine. So maybe the problem is actually that the chain root parent pointer seems to be null. Let's check this thing. Chain root that pp is equal to null pointer. So if this thing is true, then okay, yeah, this seems to be the problem, and that's annoying. But like very annoying, because this should never happen. Okay, so that's pretty bad. So I have a feeling that this may happen because we have messed up some links somewhere, and it may happen that the chain root is actually equal to the parent chain. Actually, wait, it's like the tree root of chain root is actually equal to the tree root of the parent chain. Or in some sense, like it may happen that we have merged the two chains in a way, which shouldn't happen. But like maybe we messed something up. Okay, let's check it out. And this indeed seems to be the case, but like that's very annoying. Okay, let's see. So this means that, so I mean, most likely like the, okay, let's see what happens actually. You know what? Let me just print the IDs here. So those should be like the IDs of the tops of both chains. So it's like it's 0 and 0. So let me go back and see what edges we are adding. So initially we are adding a 0, 0 edge. This is like an additional edge, so it won't be in the tree, in the linked tree. Then we are adding a 0 to 1 edge, which is still fine. So we have like just a 0, 1 there. Okay, yeah. So yeah, that's the thing. So now we are adding a 1 to 2 edge. So the first thing that happens is that we should access 0. Oh wait. Oh no, we are accessing 1 initially here, and 1 is in a component with 0. So okay, that's weird, because like, when we added them, maybe I actually messed up the link. So let's see. So I did reroute to U. So it's like, oh wait, why am I not pushing the reverse here? I forgot to like actually update the flag here. So that's like a definite mistake, but maybe there's something else too. But I mean, that's definitely wrong. Okay, so what I did was basically I accessed U, I rerouted it to U, so now we have like a single vertex of U, then we have like a single vertex of V, then the parent pointer of U was V, and basically like we incremented the size of yeah, that's pretty much it. Yeah, but it didn't fail there, so I think I'm messing up some parent pointers, like most probably. Actually, let's check the pool, because it's one of the functions I'm using. So yeah, this thing ensures the normal parents. Okay, that's fine. Then if left exists and the parent pointer of left also exists, then I said, oh wait. No, actually, never mind. I shouldn't touch the parent pointer here. Do I initially set them up to null? Yeah, I do. So that should be like that. That's again fine. I also have the ID and everything. Okay. So this looks nice. Okay. I just hope I didn't mess up the merge somewhere. Did I mess up the merge? So push the left and right. If the left priority is greater than the right priority, then I unite into left right with left right and right. Yeah, that's fine. And then the return will be left. Yeah. Otherwise I merge the left into the right left with left and right left, and yeah, the answer is right. Okay, let's see the split. If so, I first push T. If T doesn't exist, but for a null pointer, yeah, that's true. Then the index is just the size of the left subtree. Yeah, that's again correct. If index is less than or equal to k, this means that basically the current node is in the left part. Then I split the right part into t dot right, the right part, And here k minus index minus 1. Is this correct? Yeah, because we have one additional vertex there. Okay, yeah, that's true. And here I just split the left part into left and t dot left, and I set the right part to be equal to t, and then because t is always the result, I just pull it. Okay, yeah, that's correct. Okay, so let's see the tree root. I mean, yeah, this looks good. So the pull up basically just fixes this thing. I don't want to call pull here, just pull. I just want to pull the component size, mostly because if I just call pull here, it also pushes the children. Like in pull I explicitly push the two children. So you know what? No, that's fine. Okay, so figured out that right now the chain root and this thing seem to be the same thing. Actually, we can have a very small example here. If I mean, so we have like the vertex for 0, that ID, no, not that ID, so it's like, you know what, actually, let's look the because like chain root should be the root of the chain, so let's actually just print the two different so it's 0 and 1. That's interesting. So okay, yeah, so it's like an axis. Actually, where does the PP come from? Yeah, I think I figured it out. So the main problem, I think, comes from the fact that so from those two couts we printed, because right now we just have a single edge and like this axis actually breaks, it seems that the t.id is basically 1, which should be like that, and like the chain root seems to be equal to, yeah, so basically this means that, so the chain root seems to be equal to, that's interesting indeed. Oh wait, what I could have done is basically, before running remove after, I could have seen the current chain of t, so it's like the size of trip that root of t, to actually see whether this size is equal to 1 or 2. Because if it's 2, then we have a problem. If it's 1, no, if it's 1, we have a problem. If it's 2, then the problem may come from somewhere else. So size is equal to 1. So yeah, that's pretty annoying, because this means that in reality the size of this strip is actually just 1, like this chain, and it has some parent pointer. But somehow after we run this thing, okay, also I'm gonna let's actually see what's the root before that. So it's like ID of the root of t, like the root in the tree, and you can see that the root is 0. However, oh well, that's not what should happen. Did I actually just mess up the parent pointers, not the PP pointers? This will be very... Yeah, I did. This is because... So, we are pulling here, right? So, okay, yeah, this is a very common mistake, which is... I'm updating basically the parents of the children to t, but I'm never setting that the parent of t will be null. So, yeah, that's a very annoying thing that can be easily missed. At least I debugged quite a lot of different parts. Okay, so it's definitely failing at some other part now, but here to... Okay, yeah, let's just remove the different COs to see until where we reach actually. At least I found one of the annoying bugs, which is good. Okay, so let's just remove them so I don't remove some part of the actual code. Okay. Not quite sure what I'm printing right now, but it's like a bunch of things. I'm gonna leave those prints, I think, but which one? Where do I print so much numbers from? Oh yeah, it's from here, I think. Yeah, it should be this. Okay, so let's actually see whether we ever reach this point of the removal, or like the cut. So with a flash, because else we won't really print it. Well, surprisingly we don't. But the weird thing is that, alright, so we first add this edge, we add this edge, we add this edge, we add this edge, and so on. Here the components are 0 and 2. And I don't think that this is the case, because like we are adding this edge. So initially we added the 0, 0 edge, then we had the 0, 1 edge, then the 1, 2 edge, and then we basically have like the 0, 2 edge. So this means that the link isn't working again, which is, as I already said, like I don't know how many times, it's quite annoying. So we do set the parent pointer here. You know what? Let's just actually print right here for all 4 nodes. So we have like 4 nodes. We're gonna print E and the parent, not the parent, but like the root of every node, so that we can actually see the connected components. So it's like link a tree that root of I. So I think it's... Are you telling me that this doesn't work? Okay, that's weird. Because this is just after the first operation, and it seems that... So we have like just one node, which we Okay, let's see what the root actually does. It's just like we access the node and then we set the ID. And initially it's just like remove after t. So yeah, basically so if like t dot left dot parent pointer is equal to alright, so it should be again in remove after. So here 1. I'm already kind of annoyed with doing everything. Okay. Here 1, here 2. Okay, so the thing about the whole thing is that alright, on the next execution of root something fails. But like those strips should have like a single node, and pretty sure that's the case. We should print here yeah, definitely that wasn't what I wanted. Wait, I'm actually printing. What's the size of sorted? Yeah, this was actually a very sad thing. It was crashing because I don't have the node free. It wasn't crashing. Yeah, cool. It was crashing because I was printing 4 integers and not 3. Yeah. Okay, so we have that the root of is basically 0 for 0, the root for 1 is 2, the root for 2 is 2. Jesus, that's the case. Okay, so initially everything has its root as it is. Then after the, so like that's when we add the first thing. So that's when we have added just the first edge. Okay, yeah, that's correct. This is when we have added just the first edge. So after that, yeah, this is wrong. It should have been like both roots here should have been the same. Why isn't it working? So I'm gonna just have it like that and like that. So the root, which is I, that's indeed the case. So So let's have some debugging coutts here. So we basically add an edge from 0 to 1, and then as you can see the roots are wrong, So why is this so? Okay, we did fix the parent pointer, so I mean, I'm just gonna try something here. So what does root even do here? It just accesses the vertex and then returns the ID of the root. Yeah, and yeah, here I actually made a small mistake. So the axis, it's not the problem. The problem isn't in the axis. The problem is in the root, because the root is the leftmost vertex in. I mean, like, basically the root is actually the first, or like the vertex with the smallest priority in our tree. So we need to get like the leftmost vertex. So we have like a temporary node, which will be like the root like of everything, and we first push the temporary node, and while we have a left child, what we do is basically we go to the left child and then we push this temporary node, and then we return the temporary node, and like not the temporary node but like its ID. So yeah, this should be it for the component size. It's still the same thing, but yeah, that's quite a big mistake actually. Something like one. All right, it doesn't crash. This is better. Okay, so let's remove the debugging coutts. Just gonna comment this thing out for now, because maybe I'm gonna use it in a bit. Okay, yeah, I had one test. Okay, I'm not printing anything, so I suppose I need to print something. So for example, like here, I'm gonna print for every left position, the right position. So it's like, all right, so it seems to work. Basically, it finds that for 0, the first position that breaks the whole thing is the third one, or like this one. Like this is the first position that breaks it. And then for basically from here, for 1, wait, which one is the one that breaks it for 1? Should it be this one or should it be the next one? Let me just think about it for a second, because I mean, actually, let's just have the roots after everything. We already know that we have only 3 vertices, so we have like I, and in brackets I'm gonna write the linked tree dot root of I. At least for the people who are watching this right now, I mean, after I end this thing, I'm gonna share the implementation, and hopefully you would be able to, like, if you have some problems with the implementation, you would be able to debug it afterwards. I mean, like, I'm gonna debug it now, but like, at least you'll have the whole implementation and you can use it as a template for future reference. So at least that's, I mean, something that's slightly positive. So yeah, we have the 2 here. Then it should be again 2, but we shouldn't go to the next one because we can't really match it there. And why is it doing this? So we have the 2 here. I mean, those will be like that, but it won't really disconnect it. Oh yeah, obviously, because we have a cycle. Yeah, it computes the right bounds correctly, as you can see. Because, I mean, for this first position, we have like the whole thing, because it's the 4 is the rightmost bound. Okay, that's a positive thing. like, I'm very glad that it's working at least. Okay, so for every left, it seems to be computing correctly the right bound. So right now we already have the size of the perfect matching, which is just right minus left. Let's just check the other sample too. So for the first position, it seems to be giving 2, so it's like this thing, and obviously that's correct because here from 1, 2 and 2, 1 we have a cycle. Then for this one, it seems to be giving 4, so it says that this is the longest one we can do, and that's indeed the case, because if we add 3, 1, we have 2 cycles. And then for everything else, like for this one, why is this correct though? We have like, oh yeah, because that's a 1, which is an additional. Yeah, that's also correct. Okay, cool. So now we are only left with counting the number of components. So because like, I mean, right now we have a correct implementation that basically just finds the matching correctly. But now our problem was slightly different and slightly more complicated. We need to find the product of the sizes. And here we use modular inverse. So I'm gonna just implement it below everything. I mean, like below the implementation for the linked. Actually, I need it somewhere here. But the good part is that actually this matching works and like the linked tree works. After quite a long time of me debugging it, and again, I apologize for being so slow with this, but again, it's like not the easiest thing, I would say. All right, so let's have like the power function, which now I'm just gonna quickly implement the math. As you remember, I mean, it was already like quite a long time ago. We basically had to find the product of the tree components multiplied by 2 to the power of the cycle components. So we have like, that's why we need basically modular inverse and for the sizes of the components. So it's like, yeah, I'm just gonna implement the power now. So it's IP modular mod. I'm just gonna quickly check what our modulo was. I think it was 10 to the power of 9 plus 7. And here we just have x. So all right, so that's like the power, and I'm also gonna have a function which is the inverse of some x, and it's literally just return power of x to the mod minus 2. All right, and now for this part, initially let's have like our variable in, let's have like our answer in just the variable answer. And like let's have like int count cycles. So obviously here wait, so yeah, count cycles should increase by 1. Here, if x is equal to y, count cycles should again increase by 1. No, actually, here the count cycles shouldn't increase by 1 because we are simply uniting 2 components. And what we should do here instead is, so if additional edges of x is not equal to -1, this means that we have a cycle. And no, if it's actually equal to -1, it's equal to -1, this means that x right now is a tree. So yeah, we can multiply the answer, which is basically the product of all sizes of the trees. We should multiply this thing by the inverse of the linked tree that component size of this x. Model mod. Similarly, we should do this thing for y, because yeah, those were the two nodes. So yeah, we multiply those two, and then after we add the edge, actually here, if the added edge, so like if we have a cycle here, we should multiply by the component size of AI. So here, let's just have, yeah, let's just have x, it's fine. So here it's not add, it's add e. You can obviously notice that in this function, the count of cycles won't really change, because we are simply adding one edge, and this edge definitely connects two different components, so it's definitely not a cycle. And here we just increment the count cycles. Oh, and yeah, okay, so we increment the number of cycles, and also we know that before this point our thing was a tree because of this assertion. So we also need to multiply our answer, or like the product of the components, by, oh wait, so also here below we shouldn't multiply by the inverse, but we should multiply by the normal thing, because in some sense we initially divide by the two component sizes of the components we unite, and then we just multiply by the sum of their sizes. And here we should just multiply by the answer by the inverse of the linked tree dot component size of basically x. All right, so that's pretty much it. Let me just quickly check, go through it again. I think that this should be it. So yeah, we handled the count of cycles and the other thing. So, all right, I mean, the only thing left to do is basically to handle the removal of basically the cycles. I mean, not the removal of the cycles, but like the removal of the edges. So, all right, if obviously if L was the additional edge, the count of cycles will just decrease by 1. So yeah, that's obvious. And here, this means that we also need to multiply the answer, because now the component becomes a tree, by basically like linked tree dot component size of root. And we need to divide everything by modulo. And in the other case, when we actually cut some edge, what we need to do is first we're going to check if the added edge was actually a yeah, let me think how we should handle this thing. So yeah, if the added edge was -1, okay, so actually there is a small mistake here. So here the match we should only match if the added edge isn't -1, because like if it's -1, this means that we didn't really have an additional edge, so we shouldn't do anything. Okay, so okay, if the added edge was -1, so this means that we didn't have a cycle in our component. We basically just need to multiply the answer by the inverse of this thing, because like we know it was a tree, so yeah. Otherwise, we know that like, because first we basically subtract the additional edge, so if it's not -1, we basically just initially decrement the cycles by 1, because yeah, we basically just take out the cycle. And now we are sure that we have a tree, so yeah, actually, if we are sure that we have a tree, we can basically just do this thing here. And now we just have, we need to multiply by not the inverses, but like the normal things for a left and a right. Actually, and b left. So this thing should be if the edge we are adding wasn't minus 1, we basically just decrement the cycles, and then we just have this thing here. We cut it, and then we multiply by the new sizes. And then, because like if the added edge wasn't minus 1, we just match it again, and this will fix up the cycles and everything by itself. Something else I forgot. All right, yeah. So here we actually, if this wasn't minus 1, so the cycles actually decrease by 1, and we need to multiply by the size of the component here. It's kind of annoying because here we have the multiplication, then we have just multiplication by the inverse of this thing. But I mean, yeah, it's good enough, I would say. So yeah, let's check it out. I mean, yeah, I'm not printing anything, so it's kind of expected that it won't work. So first, let's have the product. So it's answer. So we need to multiply the answer, which we are gonna just print on this. This time it's basically answer multiplied. So that's like the answer we need to print. Multiply by power of 2 to the power of count cycles. However, we need to remove the number of cycles that are like just self loops. So like the cycles that have AL equal to BL. So we have like another variable, 1 cycles, and everything, modulo mod. And like this 1 cycles are basically handled here. I think the Q undo trick overkilled this question to another level. I mean, initially the main idea was to have this solution pass, so like you have to actually do the subtree. I mean, you basically had to do link cut with subtree handling. And honestly, normally you wouldn't really implement this thing from scratch, but at least when I was learning link cut trees, the problem I found was that, I mean, I could use a lot. There were like some implementations online, but I mean, it's kind of hard to understand how the people are doing the things and why they're doing them. And yeah, basically that's the main reason I'm doing this video. If you look at the implementation, you don't really understand some part, so you can refer to the video, although it's like extremely long now, which isn't ideal, but yeah, I mean, that's the best I could do. Apologies. Hope it can be used at least for something, like if you have some trouble implementing linked trees. So yeah, so I'm just handling here the final part, which is basically the 1 cycles. And yeah, if we can match, then the 1 cycles will increase only if the A right is equal to B right. And then after we remove the edge, we basically just decrease this variable by A left is equal to B left. Basically, we only remove in this case. And I think this is pretty much it. Let's see whether this sample will work. Oh, it doesn't. Oh yeah, that's because the answer initially is, so answer should be equal to 1 and the count cycles should be equal to 0. And it's not working, which is pretty bad. Let's see what's the answer here. Then what's the count cycles, and then end line. I mean, at least the count cycles are handled correctly. So let's see what happens. I think the problem comes from the inverse right now. Let's just see what will happen if I how do I implement the power? Is it correct? Oh yeah, because like the power in the power I actually multiply by p and not by x here. Cool. So that's not correct. Okay, so it basically says that the answer, so in the first sample, for the first position, we have like those three. And the product should be actually, I mean, it shouldn't be free, most definitely. Did I mess up the component sizes? If that's the case, it would be so annoying. Okay, so I mean, let's just see for 0 to how much versus. So I think in this sample we had 1 to, I mean, again 3 vertices e++. So let's just print the information about the current vertex, and then its root, which is link at tree dot root of I, and then finally link at tree dot component size of I. And yeah, let's have this test, which is 1, and then this thing. So initially we have, like, after the first match equal to false, we have like 2 components. Okay, so it seems that the component size is the only thing that's wrong right now. And let's see why it's wrong actually. So yeah, it seems that so somewhere, yeah, let me try finding the mistake now. Somewhere here where I actually increment or decrement the count pp, I have a mistake. So basically what I do is, right now, pull up v, okay, so yeah, that's correct. Let me check the pull up actually. So component size is equal to the basically the component size of left plus the component size of right plus the current node, that's correct, plus t dot count pp. How did I initialize this count pp? Actually to 0, that's again true. And component size should be 1, that's indeed true. Okay, so what I did here, so where do I change the component size? I change it in 2 functions. The first one is here. Oh wait, is this true? So what does remove after do? So remove after removes basically everything after t, and this means that okay, so alright, so this means, I mean, somewhere I don't really decrease the count pp because the numbers for count pp were quite large, so I suppose it should be somewhere here. So parent chain that pp is equal to null pointer. Okay, yeah, that's correct. And chain root that pp. Okay, yeah, so this thing actually doesn't really change. We don't really use cut there before that, so yeah, we should only look at it in that's kind of annoying. It's free. Let's just print what's the component size of chain root here. just to make sure that we okay, so what happens here is it's always 1. I mean, that's the first thing. I mean, they're still calculated wrongly. Okay, so this component size here is 1, which indeed is the case because we just have 1 edge. It should be 2. I mean, like, this value should be 1, indeed. And when we access one node, then the other thing, we can just check actually the cout component size. Actually, no, we can go to chain root parent pointer that count pp, because that's the interesting value. Okay, I printed something wrong here. Oh yeah, so did I actually stop the other print? No, I don't think so. Yes. So it's always 0 here. That's interesting. Wait, so in the end, here we will have pp equal to null pointer, like after this thing ends. Actually, so this thing should be 1, this thing right here should be 2, this should become 1 after that. Let's see. So the numbers that are printed should be like, so this should be 1. No, this should be equal to 0. This should be equal to 1. No, actually, should it be 1 or 2 here? Here it should be equal to 1, actually. Yeah. So let's check. Although that's not really the first axis, I think. No, it's exactly the first axis. So 0 is equal to 0. Okay, yeah. Okay, great. So I found the problem. Seems like pull up doesn't work. And yeah, I actually know why it doesn't work. It's because we don't really apply this thing to the final root. So yeah, because like, I mean, we could have just stated it as t, while t, then we basically just pull this thing while I wasn't doing it. Okay. This seems to be the problem. So it's 2, 1, 1, 1, 1, 2. Okay, yeah, it seems to be working. Wow, after so much pain, it finally seems to be working. Let's check it on 2 samples. Okay, it wasn't with 1, 2, 3, 2, 1, 2, 3, 2 indeed, and then 2, 1, 1, 1. Okay, it's working on those samples. Let's just print it with an interval. And then indent, and print end line here. Okay, so it seems to work. Let's try submitting it. So, okay. And let's submit it. Okay, so I mean, it's kind of, yeah, those solutions though. Okay. Are you serious? Okay, it's a runtime error absolutely everywhere. So that's kind of weird. All right, so I think I had some tests from before, so let's try running. Actually, let's look at this test, which is, does it follow the format? Yeah, it does. I mean, yeah, okay, so let's run. Okay, the thing is it doesn't seem to crash, which is maybe because of the memory limit, but I doubt that. Because it gives runtime error on absolutely all tests. Someone else seems to have the same problem. So yeah, this time it seems to be running for longer, so maybe it won't be at least a memory limit. I mean, like, it's possible that it gave wrong answer because no, it's again like that, which is quite weird, I would say. Wait. Let me see. All right, so at this point, I think I might actually have to like stop this video. Like, let me just, I mean, I can easily check whether it's correct actually, because I have implemented a very similar solution before that as the I mean, like the initial solution. So let's just check whether the initial solution would work. I mean, it follows the same lines, but it's different. And it seems to be actually shorter. Yeah, but I mean, it's same size, I think. If this again gives runtime error, although I kind of doubt it. Yeah, so I mean, as you can see, I always tend to implement the trips and everything in a similar way. Yeah, but here I have like a couple of functions actually, not everything. Yeah. So yeah, let's check whether this will actually pass. Well, it did, which is unfortunate because it means that we have another bug. Okay, so Alright, so let's actually... I'm gonna spend just some time to check whether it's something obvious, like the problem. The thing I kind of... The thing that annoys me is the fact that it works, at least in the sample, and I don't really have... And also, like, one of the larger tests I had, like, I have it locally, so... Yeah, that's a bit annoying. So... Yeah, I mean... Let's actually see. So, like, if it was giving a wrong answer, I understand, but it's giving, like, some runtime error. Okay, so... Wait, so that... Oh, wait, that's the wrong solution. Let's see the correct one, actually. Oh, that's again the wrong one. The correct one. So actually, in the correct one, I decided to use a merge function that basically just merges two of the trees. Well, here I actually didn't use the merge function. I implemented this by myself, like here. Basically here we have like the parent pointer of the final thing. I set both of them to null pointer initially, then I merge into chain root, like the parent chain, then the chain root, and then I just explicitly set the parent pointer of this new chain root to pp. So yeah, that should be correct. Yeah, I mean, so the thing about root, it's actually that here we need to also I don't really have a lot of differences between the two. Okay, so in link, oh yeah, so that's how I actually, that's why I mostly use the merge tree functions in link, because like in link we again merge two trees, so we might have as well implemented it like that. So yeah, basically we reroute from the first vertex, then we access it, then we access the other one, set the pp to that one. Okay, well, that's also valid, and we just increase the count pps for v to basically the component size of u. We pull this up for the cut. Yeah, I mean, it's basically this thing. I think I have the cut. Well, I actually use some other function which is like remove left, and yeah, it's pretty much the same thing. I first reroute, then okay, so the v.pp becomes null pointer. Yeah, honestly, I think I'm gonna probably just sit and debug it by myself, like, because I mean, I'm gonna write the implementation here if someone is interested, but like, that's the thing I hate about link cuts, is that it's very good to actually know how they work, but when you sit to implement one, it's kind of annoying. Yeah, I also apologize for the whole thing. I mean, I planned it to be like better, but it seems that it didn't work out that well. Still, I mean, yeah, for now I'm gonna just give up. I'm gonna just show the actual solution, which is pretty much the same thing. So yeah, I mean, like if I have to show the implementation, like again, basically we have the trip in the beginning, then we have like the functions for the trip, which are like the push, the pull, and so on. And we always try having the parent pointer in the root. And yeah, I mean, we basically just have to remove left and remove right. Yeah, I mean, sorry about that, guys. Like, probably I'm gonna just write in the description or like in the comments of this video what was the problem, like in an hour or something like that. Because like right now I think there's just no point in you watching me debug some of the small details. And yeah, hopefully you got the concept. And yeah, I'm glad if I could help someone in some way. And yeah, I guess thanks for watching. And yeah, stay tuned for the next contest by CodeChef, because recently they have been pretty good, at least in my opinion. I mean, there are some very interesting problems, like, and the quality is definitely improving. So yeah, thanks again, guys. And yeah, if you have some questions, just you can either put them in the comments or message me on CodeChef, CodeForces, or whatever you feel comfortable with. So yeah, thanks guys, and bye for now.